everyone, and welcome to the video. We really hope you enjoy this tutorial. Happy learning!
Yeah, that's just run entirely on my local machine. Without any API keys, no internet connection or any subscription, just using my GPU, Python and a model called GPT-SoVITS. So in this video, I'm going to show you how you can make yourself a local AI voice assistant that completely runs locally on your system and speaks in custom voice for any specific character you choose. So with that, let's get started. Okay, so before moving into coding, let's get a picture on how the system actually works. So step 1, the user types something. Then step 2, that the input is passed into the local LLM running on our system. In this case, I'm using Gemma 4 through Ollama to generate a response. And then the response generated by the LLM is fed into the GPT-SoVITS, which synthesizes the audio of the reference audio we provide. Then we use a sound device to play the audio. So the key here is everything runs locally, so your data is not getting stolen by the OpenAI or other companies. Now, why do I am using GPT-SoVITS? As it's one of the best open source TTS models which can use for free and run locally on your system also. You just need a 3 to 10 second audio sample and you can get almost 99% accurate audio clone. So now that we have an idea, let's move to the next step. Okay, so let's look into some hardware and software requirements before we start. So for the best performance possible, make sure you have a CUDA capable NVIDIA graphics card, so like a 3050 and plus. Make sure at least you have 6 GB VRAM available on the graphics card, and in your local system, make sure you at least have a 8 GB RAM for the synthesis to be more faster, and you should at least have 10-20 GB space available on your disk for downloading the models, etc. So those were the hardware requirements. And the softwares, make sure we are going to be needing Python 3.11 for this project, and make sure you have Git also, so you can clone the repo of GPT-SoVITS. And I'm not going to show how you can get GPT-SoVITS on your system again, because I already have made a video on how you can locally run it. I will mention that link of the video in the description. You can just watch it to download GPT-SoVITS. Second, you are going to be needing, if this is for those who are running on this on an NVIDIA graphics card. So check the CUDA version which is going to be available on the system. Wait, I will just show the CUDA versions that we need for this. So just head over to GPT-SoVITS GitHub, go down and check the tested environments. So they have mentioned the CUDA version use. So in this case, I'm going to be using CUDA 12.8. Before downloading the CUDA, make sure your graphics card supports that CUDA version or it will not work. Make sure your PyTorch and CUDA version match is what you're downloading. So I'm also not going to show how you can download CUDA. Just search on the internet, you will find some videos how you can install CUDA toolkit. With that, let's get started. Now let's get the local LLM. So we are going to be using Ollama for getting the model. So just press on download for Windows and get the executable file and just install it on your system. After installing Ollama, head over to your terminal and run this command, Ollama run, and the model name. So the model in this case we're going to be using is going to be Gemma 4, specific Gemma 4 E4B, as this is one of the lower end models, but it still has a good reasoning and context window. So I'm going to be using Gemma 4 E4B, but make sure your graphics card and memory have enough space for running the models. If you have more memory and more better graphics card, you can run higher models also, but in this case I'm going to be running Gemma 4. You're happy to try other models also like Llama, they are also good. So just copy the name, head back to your terminal and just paste the name and enter. So this is gonna, for your case, this is first gonna install the model. So you could have just used Ollama pull then the model name, it would have downloaded it, but I would say just use run command, so it will download and run it at the same time, so you can check if everything is working fine. Let me say hi. You see it's working. So with that, you got the local LLM. Now let's move to the coding. Let's start with the file paths. So these are just the constraints that we are going to pass so it can locate where the model exists and where to use it from. And we are also going to be providing the reference audio part and the reference text part, so you can use those also. So make a file paths.py and then add your GPT model path, SoVIT model, and your reference audio and reference text. So first is going to be the GPT model path. So I'm going to go to the GPT-SoVITS and then again GPT-SoVITS, then in the pre-trained model section, and grab a model models. So in this case, I'm going to be using the V3 models. So S1 V3 CKPT, this is the GPT model, and S2G V3, and these three are the SoVIT models. So just get the both the path for the V3 model and the SoVIT model, and make sure the paths you added are with raw strings, so it doesn't conflict if it's an escape sequence. So with that, add the other two parts also, your reference audio and reference text. After adding all the parts, so now let's move to the next one. Okay, so we are now going to be working on the script which will help us in creating the audio. So make yourself a audio synthesis.py, and here, so let's first import the modules. So first import OS, this is going to be required. So after importing OS, we need to change the directory of our current location to the GPT-SoVITS folder. Just OS change directory to GPT-SoVITS, this base location, because the thing, the model we are going to be using is going to be inference.py, and as this file exists in this directory, it's going to check the local current directory for the file if it exists. So because we change the directory, it will see this exists and it will let us use the function. So now just use os.change directory and add the name of the folder the GPT-SoVITS is currently in. So in my case, it's GPT-SoVITS, and now we're going to be importing the next part. So from GPT-SoVITS.inference.webui, we're going to be importing change GPT weights. So these are for adding the GPT models, then change SoVIT weights for SoVIT model, and get TTS wave. So this is going to help us for the audio. So after that, now let's move to the next step. Okay, so now let's define our TTS class. So I'm going to create a class. We call it GPT-SoVITS TTS, you can name it anything. And in here, first we are going to be adding a class level variable. So our models loaded, and we're going to set it to false. So this flag is going to check if the models are already loaded once, so we are not going to be loading it again. So every time we create a new instance for this GPT-SoVITS class, we don't need to reinitialize the models, and this is going to save us a lot of time. After that, let's make a constructor for our other variables. Okay, so now let's work on the constructor. So I'm going to make the constructor, so def __init__, and give the parameters GPT model, SoVIT model, reference audio, and reference text. After adding those parameters, let's add one more. So this is going to be the language. So language you're using for your audio sample, and the reference text. So in this case, I'm going to be using English. It's time to make the variables. So we're only going to be needing three. So reference audio, reference text, and language. So make for these three. So self.reference audio, and do it for the other two also. After that, we are going to check. So if models are not loaded, then we are only going to load the models. So this GPT-SoVITS TTS class dot are the models loaded. So we're going to be checking. So if they are already not loaded, so we're going to now load the models. So I'm just going to give a message print loading the models, and then just call the change GPT weights, and then pass the GPT model, and then call the SoVIT weights, and just pass the SoVITS model. After that, we can just give a message models are already loaded. After that, we can just change this flag our models loaded to true, as the models were finally loaded. So GPT-SoVITS TTS dot our models loaded, just change it to true, as after the first instance the models are loaded and we don't need to reload them. So that we are done with the constructor. Now let's move to the generate function. Before that, we can just pass a message if the models are already loaded. So we are just gonna say models are already loaded. Okay, now let's move to the generate function. Okay, so make a generate function. So def generate. So we are gonna take a text and a speed. The speed is optional. In my case, if I want to change the speed of the audio that is generating, you can just change it from here. After that, make a results variable. This is gonna store our audio. So just call the get TTS wave function, and then let's pass the parameters that it requires. So first, pass the reference wave. The reference wave is just the reference text, reference audio we're gonna providing. So just provide the reference audio, self.reference audio, and pass the other things also. So for next is gonna be the prompt language. Prompt language is this gonna be the language for the reference text and the reference audio we are providing. So this is gonna be self.language. So in this case, this is gonna take the English, and after that, let's move to the prompt text, which is reference text, and then just we are going to be providing our user text the user input. So text is gonna be text, and we need to also provide the text language also. After that, we're gonna provide some more parameters. These are optional, but you can add them. These parameters are just to make it more realistic and more natural. The sample steps you can tune on your own. The lower the sample steps means that the generation is gonna be much faster, but it might feel a little more less natural. But in my case 8 works fine for me, so I put it at 8. But if you are feeling like it's more robotic or the audio is getting muffled, you can try increasing it. So after that, now we need to somehow return this. We directly cannot return the results as this returns us in a generator, so we can't directly return it. So we got to iterate through this generator and get the final sample rate and waveform of the audio to like actually play it. So we're just gonna make a SR and a wave variable, and I'm gonna assign them to none. After that, just use a for loop. So for SR comma wave and results, and we are just gonna pass, so get the final value for SR and wave. So just now return the SR and wave. So SR and wave. Now we're done. Let's put everything in a try block also, so if any exception occurs we can check. Now we are done with the audio synthesis, and then now we can move to the next step. Okay, so now we're going to be working on the main.py. So first we're going to be requiring some modules, so just open your terminal and install. Make sure you're using a virtual environment. So pip install. We're going to be needing LangChain Olama and sound device. I've already installed, so it's already saying I've already installed this requirement already satisfied. Right, so after that, now let's import the modules. I'm going to import from LangChain Olama. I'm going to be importing chat Olama for getting the chat instance started. So after that, I'm going to import sound device as SD, so we can play the audio we generated from there using the sound device. So after that, just call the from the audio synthesis, we're just going to get the SoVITS class, the TTS class. So from audio synthesis, import GPT-SoVITS TTS or whatever you named it. After that, we are going to be importing from file paths the paths, so we can pass it to the GPT-SoVIT. After that, we're also being importing queue and thread. So queue and thread are going to help us in parallelly generate the audio while providing the text one by one. So from queue, import queue, and from threading, we're going to import a thread. So we need these two because if the LLM provides a big text, it's going to take a long time for it to synthesize the audio. So what we're going to do, we're just going to split the text in punctuations. From every punctuation it creates, we're going to split the text, and we're going to pass this text in chunks, so the generation is much faster. After importing the modules, let's initialize the class. So first is we're going to make the TTS class. So TTS is equal to GPT-SoVITS TTS, and now let's pass the paths. So GPT model is just going to be GPT model path, SoVIT model path, reference audio is going to be reference audio, and reference text, we directly cannot pass a text path here. We need the actual text. So we're just gonna extract the text from the text path. So front of the GPT-SoVITS, so I'm just gonna call with open reference text or path. Let's open this file in read mode, and we're just gonna read the text. After reading, we'll just pass it to here. So reference text data. Okay, so now that we're done with that, let's make a instance for Olama. So I'm gonna make LLM equal to, I'm gonna call the chat Olama, and then let's pass the model. So the model is gonna be, in my case it's Gemma 4. Make sure the model name you give exact one you downloaded. So in my case it's gonna be Gemma 4 E4B, 4 billion parameters, and we can add a temperature also to get some randomness. After that, now let's move to the next. After that, add a response function. So this is a function for the LLM's response. So this takes the user's text and a message array. Message array contains a system message and human message. The system message you need to edit a little because as LLMs really don't understand complex structures like markdowns, dashes, or tables if the model creates. So we are telling the model, so respond in plain process only. It shouldn't use any markdowns, dashes, or asterisks, so like we don't get any like unnecessary keywords in the response, and we should keep the response concise and conversational, so like it doesn't get too long also. And after that, we are just returning the invoke message with the content. So now we need to make the function for cleaning the response that we got from the LLM. So now you need to make a clean TTS function. So I'm going to explain how this function works. So first you're going to be requiring RE. So if you don't know what RE is, RE stands for like Python's regular expression module. So what is regular expression? So this RE helps us to like in searching, matching, or manipulating text using regular expression. Is basically just looking for, we are looking for patterns in the text and we are replacing them with anything else by setting some rules. I'm not gonna explain how regex works in this video because it's gonna be a topic for a whole new video, and it's not really relevant enough. So we're just checking for pattern and we're just replacing and cleaning the text. So first, using re.sub, we are looking for a substring which contains a asterisk, a bullet, and a dash, and we're also checking for if there's extra space after it, and if we find those things, we're just replacing them with nothing and we're applying it to the text. So this removes the asterisk, star, bullet, and dash, and after that we are also removing the markdown and a space after that. So using markdown, and we're also looking for if there's space, so plus space, and we are also changing it to none. And we're also checking if there are some extra spaces, because in some situations there are 2-3 spaces in the middle. So this looks for 2 or more spaces, and we're just replacing with it 1 space. And after cleaning, we're just returning the text. So that's it with the clean TTS, and now we can move to the chunking. Now we need to work on the chunking function. So why do we need a chunking function here? Because like we directly can't pass the entire text to the LLM. If like even after cleaning the text can be huge, and it still might take like a long time for the synthesis to fully complete. So what we're going to be doing is splitting the text in different in punctuations and passing the text in chunks to the LLM. So the inference process stays much faster while comparing if we pass like a full string. So I'm going to make a function. So the chunk, let's name it chunk text, and assign these parameters. So let's just say what these parameters do. The text is a text input we are going to be providing, and the first chunk max, this is the max size of the first chunk we are generating, is 60. So why we did this? Because like when the LLMs like the models are loaded, we kind of expect the first result to like a little bit faster. So like if we pass a big enough chunk, it might take like some time. So for the first generation, we always try to keep it less, and the rest of the generation can be bigger also. So it will feel much faster, and it's in a continuous flow if the first chunk is like small and the rest of the chunks are a little bigger. So I hope you get that. So after that, now let's move to the next. So now we're going to be making a sentences variable to store the chunks. So make a sentences variable. Then we are using re to split the text whenever we see like a full stop, a exclamation, or a question mark on the text. So after that, now let's move to the next. After that, now we are going to be making a chunks list. So this is going to be storing our finalized chunks that we will generate. So after the chunks list, make a first flag. So this is going to check which chunk we are currently working with. If the first chunk, we are assigning the limit to 60, and if the other chunks, we are assigning to 180. And also make a current string variable. So this is gonna store strings temporarily while we are working on them. So now let's start. So I'm gonna make a for loop. So for s in sentences. So after that, we are gonna be adding a limit. So make a limit. So by default, the limit is gonna be first chunk. So if first is true, or else if the first is false, then we are adding the limit to be 180. So the rest of the chunks. So after assigning the limit, we need to check a condition. So if the length of the current string we are building with the length of the chunk we selected, we are in the loop. So if those two combined length is less than the limit, only then we are going to be adding that current chunk to the like the current string. So if this condition is true, then we are only just going to add it. So current plus equal to s, and after like the chunk, just add a space for the next one. So after that, so if we need to make for if the chunk, the length of the current and the length of the current this is greater than the limit, now we need to work on that. So use the else block. So if it goes over the limit, we're checking if there's something in the current chunks. We save it and we add it to the chunks, and we then change the first flag to be false. So now the first is done. So we are going to be working with the other ones, and then we are going to be starting with the new chunk in the the current. So we are changing it. So that's with the chunking text. If we see it's less than, we are storing it in the current, and if it's like greater than, we are just storing in the finalized text and moving on to the next one. So after the loop is done, just get out of loop, and we're just going to be adding some condition for some checking the leftovers. So if there's something left, we are just going to adding it to the final chunk in the chunks list. So chunks dot append, then the current. After that, we're just gonna return all the chunks. After that, now make a generate audio chunk. So we're going to be using this to generate the audio parallelly. So just make a generate audio chunk, which is just calling the TT to generate the audio. So after that, now we're going to be making a stream function for streaming the audio parallelly. So I'm going to create a function stream responses. This will take the response, and then we're first going to be cleaning the response that we get. This is the response is going to be the actual message. Actually name it LLM response. So first we need to clean it. Clean response. So just clean res equal to, we're gonna be first calling the clean TTS and then pass the LLM's response. So we get a clean text. So after that, we need to chunk them. So name it chunks, and then we're gonna call the chunk text function that we made, cleaned res that we got, and also we're also gonna stripping it, so like removing like any starting and trailing white spaces. So if nothing is generated, so if no chunks, we're just gonna say no chunks to synthesize, and then we can just close the program using a return. After that, make a audio queue. So this audio queue is going to help us in storing the audio, and we'll be using that to play the audio parallelly by passing one by one to the like sound device. So audio queue is equal to queue, and we're going to set the max size to 3. I'm going to explain why we set the max size to 3. Okay, after that, we need to make 2 threads. So one is going to be a consumer and another is going to be a producer. So the producer is going to produce the audio and consumer is going to play the audio one by one. The max size is 3, so that the generation and the playing of the both threads doesn't go too far, and it's going to save some space also by keeping it max size to 3. So now let's first make the producer and consumer function, then we can use threads on them. So first make the producer function. So def producer. Before actually making the producer function, we need a special object. So we're going to be requiring a sentinel object. So let's quickly make one. So what is the sentinel object? So this sentinel object is a special kind of object that we are using it as a signal. So basically this object is gonna signal our consumer that we are done with like playing the audio. There's nothing in the queue and we can stop. So we're just using it as a signal. So after making the sentinel object, let's work on the producer. So make a producer function. So producer, and it's gonna be taking out chunks and our audio queue. Spelling. So for chunk in chunks, we are going to generate them one by one. So result, we're going to call the generate audio chunk and then just pass the chunk. So like if we get a response, so if result is not none, we get something. So we are going to put it in the audio queue. So dot put the result, and if we get none, so it is done. We are not getting anything. So we are just gonna be putting a sentinel object in, which is gonna just tell our generation is done. So just put it outside. So audio queue dot put the sentinel object. So while we are getting the audio, we are putting it in the audio queue as the result, the audio, and if we get nothing, we're putting this as a sentinel object to point we are done. After that, now let's make the consumer. So I'm gonna make the function the consumer. So this is gonna take the audio queue and the total amount of chunks we are playing. So just show like how many chunks are left. So it's always gonna be starting with 1. So the I am gonna initialize to 1. Then we're gonna run an infinite while loop that's gonna play. So while true, we're gonna get the item. So make the item. So we're gonna be getting the item from the audio queue. So this is gonna get the first item, as the queue is a FIFO format, the first in first out. It will get the first one. And if we see if the item is like a sentinel object, so we are just gonna break the loop that there's nothing more and just print what we are currently playing. So currently, and we are just gonna unpack it. So sample rate and audio, which is gonna be the item that we got from the audio queue, because as it's in a sample rate and waveform, we need to first unpack it. So using SR and audio to unpack it, and then we're going to be using SD to play the sound device to play the audio. So sd.play the audio and the sample rate, and we are done. After playing one audio, we should wait for 1 second. So just wait and then just increment the counter. So we're done with the first one and we're moving to second one. So that's with the consumer one. Get inside the stream audio and create 2 threads. So I'm going to name them T1 and T2. So T1 for the thread, and this is going to be targeting the producer, and the arguments we're going to be passing are the chunks and the audio queue. After that, make another thread, which is a consumer. So thread target this time is going to be consumer. Then we're going to be starting the first thread. Then after the first thread, then we're going to be starting the second, and we're just going to join them. So T1.join and T2.join for the next and then we're just gonna join them. So the main program is gonna wait for both of these to finish before moving to the next one. Yeah, so that's it. We are done with the stream audio, and now we need to we need to call the LLM and get a response. Okay, so I'm gonna make a simple function to just test it. After that, just call the stream audio and just pass a response. So stream audio, and the response we got. So here it is, and that's it. We're done, and it's time to check if everything is all right. So now, first, before running, make sure you have Ollama running in the background. So I'm just gonna open Ollama. Just start it once, and it will be started. See, it's running in the background. Now we can run the file. Okay, so just run it. The first time it should initialize the model, so it would take like a little bit time, but after that, like, it would be much faster. Oh, wow, okay, perhaps for, oh damn, frick. Okay, where? Oh, I'm blind. I'm a genuine blind. Okay, just save it. If I messed up a comma also, and let's rerun it. Test number 2. Okay, it came, so it's initializing the models. So let's just wait. Yep, it's time to ask. So let's just ask. What should I ask even? Okay, explain CNN and short. Let's see how it does. So this is a big one, so we need to wait for the local model to generate first. Okay, the local model gave the answer, and let's see. Yeah, it started.
Convolutional neural network, or CNN, is a type of artificial intelligence designed specifically to process data that has a grid-like structure, most famously images. Instead of treating an image as just a massive collection of numbers, a CNN learns to recognize patterns within it. It works by using small filters,
It's actually
or
quite
kernels,
accurate,
that slide over the image. These filters detect specific features, like edges, corners, or textures, in the initial layers. As the data passes through more layers, the network combines these simple features to recognize increasingly complex.
Okay, that was quite accurate. And that's it. You have successfully built yourself a local AI voice assistant with custom voice running entirely on your system, completely offline. So that's it for today's video. Make sure to leave a like, subscribe to our channel, comment what you want next, and I will see you in the next video. Bye.